Hello everyone, welcome back to one more interesting question on collisions taken from Pathfinder again. This is simple but useful for JEE examination. Let's read it. A container of mass capital M equal to 10 kg containing small m equals to 1 kg of ideal gas. 1 kg ideal gas is pretty high, but anyway, and this entire container is released without initial velocity from a height h naught equal to 12.1 meter. Okay, dropped. If collision of the container with the ground is perfectly elastic, okay, how high above the ground will the container bounce? So bouncing off they are talking about. Neglect air resistance and assume that all internal fluctuations, this is important, assume that all internal fluctuations in the gas damp out almost in no time. So if there is a relative velocity between gas molecules and container, I am talking about ordered motion, that will just damp out or dissipate immediately in no time. That's the assumption they are talking about. It's like elastic, perfectly inelastic collision kind of a thing. So let's try to understand it as we go on. And acceleration due to gravity they had given. Okay, now, so concept 1, simple concept. When you consider gas molecules, alright, when you see gas molecules, they are having all kinds of random motion, very large amount of random velocities, and also ordered motion because of the container there. So if you calculate momentum of the container, momentum of gas in the container, you need to calculate velocity of each molecule and multiply with mass and then sum it up. When you do that, the random motion would not contribute to any momentum part there. Net momentum due to random motion is 0. Only the ordered motion will contribute to momentum there. And they are saying that ordered motion of the gas equal to ordered motion of the container, because in no time that fluctuations will get damped out. That's the assumption there. So if the container goes down with V naught velocity, the ordered motion of gas molecules is also going to be V naught there, and that is why momentum of the gas is equal to mass of the gas into V naught velocity of the container. So that's a simple idea, we have it. Now here the idea of successive collisions we are going to use here. So first thing is container hits the floor, but gas will be still continuing to go down. Then as the container goes up, it will collide with the gas molecules, and that's a second stage of collision. It's not a single collision, multiple microscopic collision, but you can take it like one big macro level collision. So it's you have one collision with the container floor and then container with gas molecules. So successive collisions you have here. We know that collision with the floor is elastic, they had mentioned it. They don't happen simultaneously because of the inertia there. So first container collides and then gas molecules collide. Okay, first collision, just before container hitting the floor, it is having, let's say, V naught velocity downward. Gas molecules are also going to have same velocity V naught downward, and so momentum is capital M plus small m into V naught is the total momentum downward. But just after collision, what happens? The gas molecules will continue to go in the same direction, but container velocity will get reversed because it's a elastic collision. It will have the same speed also. Okay, so this is just after the collision with the container. So I hope you understand up to there. So we had only one collision completed now so far. Now the next step will be, now the container is going up with V naught velocity initial. The gas molecules are coming down with still the same V naught velocity. Then there is a collision between molecules, extra collisions over and above that random motion because of the difference in relative ordered motion. So these collisions, whatever you have, that ordered motion will get dissipated in no time. That's what they are talking about. So we can treat it as one macro level inelastic collision, because after that gas and container will go together with common velocity. When they go with common velocity, we say it is perfectly inelastic collision. No? So it's like entire gas is coming down initially with velocity, but after collision it is going along with the container with the same velocity. That way you can visualize it. So now during this collision with the gas molecules, the gravity will give impulse. Of course, even during collision with the container also there will be impulse due to gravity, but the duration is so small that impulse due to gravity, which is because we know that gravitational force is a non-impulsive force, finite amount of force. So you can neglect the impulse, the change in momentum due to gravity there. Okay, so we use conservation of linear momentum during the second collision. Second collision is between gas molecules and container. I again repeat, it's not the single collision with gas molecules, it's a microscopic so many collisions, but I am treating it as one macro level collision between gas and container. So between these two, if I conserve linear momentum, approximately just before collision is capital M into V naught and small m into V naught minus, because container is going up, gas is going down. and after that gas and container together will go with common velocity, with v velocity. So we get velocity of the container after this second collision is completed with gas molecules. Now height rise, now it is going to go together as a combined as single rigid body, neglecting that random motion. So it goes to a height h dash equal to v square by 2g, and you can substitute it, you will get that it is going to be capital M minus small m by capital M plus small m squared times h naught. So you don't need acceleration due to gravity. You will get it as 8.1 meter as the height. So it's interesting, you see, if there was no gas, what would have happened? Container falls from 12.1 meter, goes to the ground with the same magnitude, direction of motion will be reversed. So again conservation of energy will get it back to the same height there, 12.1 fall, 12.1 rise. That would have been the situation. But the collision between gas molecules and container is inelastic. That's why there is a loss of mechanical energy. So there's you see, that's why height rise is going to be less there. So the loss in mechanical energy also you can calculate. You can convert that. You can see that how much thermal energy is produced and so on. But anyway, this is an interesting question that we have here. I hope you understood and you liked it. If you have any doubt, I'll be very happy to explain it. So please let me know. With that, I'll conclude, and until next time, goodbye.